This mini lecture is going to begin the idea of rotational kinematics. And so we're going to look at not how an object moves translationally in the kinematics that we've looked at in the past, but we're going to look at how an object moves rotationally and how can we describe the motion of an object moving in a circle along a circular path. And so just like with translational motion, we can identify different ways to describe that motion, what we call the players of motion. And the first one is how far does it go? Literally, how far does this object travel as it moves around a circle? So let's look at what we mean by an object moving around a circle. So imagine that you have a turntable, and it rotates about the center, and we have an object at the edge of that turntable. And as I spin the turntable, the object rotates about that point. Well, if I start to spin the turntable and stop it, the object has motion in a circular way, in a rotational way. And so how far does the object travel in that amount of time? So let's say that I turn the table a portion of the circle. So this is our amount that the object rotates. Now there's two ways I can describe this rotation. I can say, well, it traveled this distance along this arc, and I can also say it traveled through this angle that it displaced. So two ways to think about how far the object travels, and we're going to elucidate those two independently. The first is what we call the angular displacement. So how far, and describing it as our angular displacement. And this is simply the change in angle that the object experienced as it rotated along this turntable. It started at some initial angle and ended at some final angle. And we know our change in angle is the initial minus the final. Now, as we think about rotation, we also consider the beginning of that rotation as the 0 point. Like where we're going to say, this is where it starts, angle 0. It doesn't have to mean the coordinate system angle 0. It's where we arrange the origin of our rotation. So the displacement really is equivalent to the angle that the object moved through. Now, it's very important in physics. We deal with displacement, angular displacement in radians. So we want to remember that our angles will always be given to us in radians. All right, well, we can also talk about how far in terms of the length that it traveled from one point to another. And that might look familiar from a geometric standpoint. We can talk about how far in terms of the length traveled, and that is our arc length. Now, if you recall from geometry, the arc length, and we're gonna talk about the how far as our arc length s, we'll use the variable s, is equivalent to the angle times the radius. So the angle through which the object traveled times the radius of its travel, of its circle. So here are our two relationships for how far the object traveled in rotational kinematics, the first player of motion. Now, let's just test that with some knowledge that we already have about the total, if an object went through a full circle. So let's look at a full circle case. We know that angularly, a full circle goes through an angle of 2 pi, right? 360 degrees in degrees, but 2 pi in radians. Now, what about the arc length if it were to cover that full circle? Well, if I use the arc length relationship, I have s is equal to theta times the radius. My theta is 2 pi times whatever my radius is. Well, this should look familiar. This is our relationship for the circumference. And if I look at one full circle, the object indeed covers the entire circumference. So this is a way to kind of confirm our understanding about how far, both in angular displacement and in considering the arc length. All right, the how far player in rotational kinematics. Good job.